So all of the work that I'm going to talk about today is joint with my wonderful co-author, Scott Neville, who is here in the audience. And the main motivation for this project comes from cluster algebras, which many of you heard about last. And cluster algebras are this beautiful framework for taking some algebraic or geometric space that you might care about and giving a combinatorial way to get a very nice set of generators with lots of useful properties. And so this was the genius invention of Sergei Fomin and Andrei Zolovinsky back in the early 2000s and has really exploded since then. But I'm going to follow in the long tradition of not explaining to you what a cluster algebra is during a talk. So we're going to kind of skip the algebraic part of it, but we are going to delve very deep into the combinatorial underpinning of cluster algebras, which is really quivers mutation. And we're going to look at this property called sign coherence, which is this neat property about how quiver mutation works and really like coefficient data in a cluster algebra. So, sign coherence is a fundamental property of the coefficients inside your cluster algebra. And what it says is that a certain local quiver structure is preserved under mutation. So it's going to be a lot of trying to understand better what this combinatorial process called mutation is on these things called quivers, which are essentially just graphs. So a quiver is a directed multigraph meaning that we can have multiple edges with an orientation between any two vertices, except we want to exclude loops and two cycles. So I have two vertices. I don't want to have arrows pointing in opposite directions between them. And given any such quiver, you can then generate a cluster algebra. So a lot of the difficulty of cluster algebras is figuring out which quiver corresponds to the space that you're trying to study. And the fundamental operation on these quivers is this mutation process. So the mutation, which we denote by mu j of q, where q is a quiver and j is some vertex. So you have to pick a particular vertex that you want to mutate at. And this is obtained by first looking at every two path that passes through your vertex. So for each two path, goes from I to j to k, and we need to consider the fact that we might have multiple arrows between these. So we have r arrows I to j and s arrows j to k. Then we are going to add arrows from I to k. In particular, for every choice of an arrow from here and an arrow from here, of which there are times as many, we will add an arrow I to k. And there might be existing arrows from k to I. So in order to not end up with a two cycle, we will cancel arrows as necessary. Okay, and then after you've done that step, all you need to do is to flip any of the arrows coming to or from j. All right, so it's two very elementary definitions here, but it turns out that you get a very deep and complicated theory when we start looking at quivers up to this mutation operation. So it becomes very hard to tell if quivers are related via a sequence of mutations. But when they are, we say that they are mutation equivalent. And when this is the case, we denote this as Q, twiddle, Q. So in general, it is expected to be very hard for whatever notion of very hard complexity theorists care about to actually determine whether Q and Q prime are equivalent via mutations. And it's a fairly straightforward exercise to check that this mutation is actually an involution. So talking about this equivalence makes sense. Right, and then just to do a quick example of this mutation, we are going to consider a quiver on 3 vertices, which I will label 1, 2, and 3. Let's make it a little big. And I'm going to have 1 arrow from 1 to 2, 2 arrows, which I'll denote by just weighting this arrow by 2, and then 5 arrows from 3 to 1. And we can look and see that if we mutate at vertex 2, then we need to consider the 2 paths through 2. So we have this arrow from 1 to 2 and 2 arrows from 2 to 3, which means that we add 2 arrows from 1 to 3. So that's going to cancel with this 5 and give us a net of 3 arrows pointing from 3 to 1. And then we just reverse the other arrows. So we'll now have an arrow from 2 to 1 and 2 arrows from 3 to 2. All right, so now we've kind of just played this little combinatorial game. And we're going to see exactly how complicated it can get in a little bit. But doing just a few steps is not so bad. And you can also add some additional data to these quivers called frozen vertices. So often in a cluster algebra, these vertices are really representing some sort of combinatorial structure. So often we'll construct our quivers based on things like triangulations or playback graphs or weaves or webs. And you have some combinatorial structure where parts of it are allowed to change and parts of it are not allowed to change. So the parts that can change correspond to the vertices that we can mutate at, which are called the mutable ones. But we can also consider frozen vertices, which are not allowed to mutate. And these are denoted by a square. And so you can add, for example, say a frozen here. And I'm going to add 1 arrow from 2 to this frozen. And then we still need to keep track of the arrows between mutables and frozens when we mutate. So they're going to follow this same mutation rule, where here I have this 2 path from 1 to 2 to my frozen. So when I mutate at 2, this is going to give me an arrow from 1 to the frozen. So I will have an additional arrow here, and then we still have to reverse the arrow at 2. So adding these frozen vertices gives you a little bit of extra data, but it also lets you constrain your mutation process a bit. And this frozen data is what is going to correspond to coefficient variables in your cluster algebra. And when we want to consider just the mutable part of the quiver, we call this Q mut. And the rank of a quiver or cluster algebra refers to the number of mutables. So the non-frozen vertices. All right. And now that we've added this frozen data, one thing that is commonly looked at is what is the relation between the mutables and the frozens. So in particular, when can we kind of get a uniform direction for a given mutable in terms of all of the frozens? So we're going to color our mutable vertices. And here, let me pull out my colors. A mutable vertex is going to be called red if it is a sinc with respect to the frozen vertices. So what I mean by this is that whenever you have an arrow between that mutable vertex and a frozen vertex, the arrow has to go from the frozen to the mutable. And we have the opposite notion, which is green, if it is a source. So you can color your vertices via this coloring scheme, and very likely a lot of your vertices will not be colored because you don't a priori have a reason to have all of the arrows pointing in the same way. But sign coherence is kind of giving you nice conditions under which you do get this agreement of directions. And so what we say is that a quiver is sign coherent if all vertices are red or green. And they can be a mixture of red and green, but you just want that each vertex is colored either red or green. And this name is coming from the fact that people often encode this frozen data in what is called a C vector. And this condition is equivalent to that C vector having all positive or all negative signs. All right. So here's a little quick introduction to quiver combinatorics. And now let's get into this sort of nice property of the sign coherence phenomenon. So one thing is that when we add frozen data, a priori, you just get to add a bunch of frozen vertices and arrows to the mutables in whatever way you want. But there's this kind of nice default way to add frozen vertices that has some nice abstract properties. And so the principal framing is where we add one frozen, call this u sub I, for each mutable, I, and then we add a single arrow, and this is going to point towards the frozen from the mutable. And this is the only arrow that involves that frozen. So we could turn this into a principal framing by just adding a couple more frozens here. And you can check that these arrows won't actually change when we mutate. And sign coherence, the sign coherence phenomenon, this is this property that it was first noticed by Fomin and Zelebinsky when they introduced the framework of coefficients in cluster algebras, so in their cluster algebras 4 paper. Back in 2007. And then it was proven in the first case for quivers by Dirksen, Wayman, and Zelebinsky. In 2010, and then in the more general setting of skew symmetrizable matrices by sort of a big paper of Gross, Hackingfield, and Zevich that proved several properties for cluster algebras, including positivity as well. All right, and so these papers were sort of all very high-powered, but the statement of sign coherence is fairly simple. It just says that if Q comes from mutating a principal framing of some quiver, then Q is sign coherent. So we can see in our example here, when you take a principal framing, we just have one arrow out from each mutable vertex to the frozen, and it's pointing away. So that means that these would all be green vertices. And sign coherence tells us, or we can verify, that when we mutate, we will also get some combination of red and green vertices. In particular, these two are going to stay green, and now this one turns red. Okay, and so this feels like a very nice combinatorial local property, but it ends up sitting rather deep in a lot of the theory of cluster algebras. So the actual known proofs, so this one of Dirksen, Wayman, and Zalovinsky for quivers, really relies on giving a representation theoretic interpretation of the F polynomial, which is what you obtain by setting all of the cluster variables to 1 and then looking at the expression in terms of the coefficient variables. This statement is equivalent to saying the F polynomial has constant term 1. And in order to prove this, they had to introduce this whole theory of quivers with potential. Right, and then Gross, Hacking, Field, and Savage is kind of this famously dense paper. And what they did is they brought this whole theory of mirror symmetry and scattering diagrams into the world of cluster algebras. And they get sign coherence by showing that a certain degeneration of these scattering diagrams needs to behave in a certain way. And so they're really using this complicated theory. All right, and then no combinatorial proof of this is known so far. So there have been a couple other proofs since these. There was some work of Nagel and Palmon-Don using things like cluster categories and Donaldson-Thomas theory. But this combinatorial statement has no combinatorial proof, which is a little unsatisfying. And not only is the sign coherence phenomenon not so bad to state, already we started from the basics. I've been able to say everything about it in just a few words, which is not so usual for cluster algebras. But it's also very necessary for some other structural things about cluster algebras that people care about. So in particular, it's necessary in the proof of the tropical duality of C vectors and G vectors. It's needed in studying what are called maximal green sequences. So this is where we're looking at certain ways to start with the principal framing and turn our vertices green or red. But in order for that to make sense, we need to make sure that they always stay green or red. And also in the construction of the theta basis coming from Gross, Hacking, Field, and Savage, because this sign coherence is equivalent to some structural property of scattering diagrams. All right. So at face value, this phenomenon is saying something about we have a property, this sign coherence property, and it sticks around when we mutate. And so if we were to start with something that wasn't sign coherent, it wouldn't really, this theorem doesn't tell you anything about that. But some might dare to ask, what happens if you just start with a quiver with arbitrary frozen data? Can we get some sort of shadow of sign coherence popping up? And so sort of our motivating question here. And luckily for us, some people were daring enough to ask this question, in particular Tomoki Nakanishi and Misha Gekhtman, one of our organizers here, looked at this question back in 2019. And you could also see this if you open up Bernard Keller's applet and start with an arbitrary quiver and start clicking around. But you might notice that even if you start with something which is not sign coherent, it often seems to become sign coherent and stay that way. So here we want to look at infinite mutation sequences. And we want to look at the quiver, which we call QMJ, which is just the quiver that you get after applying the first J mutations to your initial quiver. And what Gekhtman and Nakanishi conjectured is called the asymptotic sign coherence conjecture. Which says that if we take a generic mutation sequence, and I'll talk more in a little bit about what exactly is meant by this generic condition, then as you do this sequence of mutations, eventually what will happen is that you will get a quiver that is sign coherent once you've done sufficiently many mutations. So this is saying that for some J sufficiently, or for all J sufficiently large, your mutated quiver stays sign coherent. All right, and this is a little bit of a miracle. Maybe not something that one would expect unless you are just playing around with these examples. And we're still sort of searching for whether there is a deeper reason why this should be true. And I want to note here that in this setting, they're allowing for adding arbitrarily many frozen vertices and whatever arrows you want between them. But actually, it is enough to only consider 2 frozen vertices, because you could just check that for those 2 frozen, or for every pair of your frozen vertices, eventually the arrow directions will agree, and there's only finitely many pairs. So it is enough to consider 2 frozen vertices. And often, for the rest of this talk, I will restrict to this case. Great. And then, what was known about this conjecture? So it is a theorem of Gekhtman and Nakanishi from the same paper. That this asymptotic sign coherence conjecture, the ASCC, holds when either Q is rank 2, meaning it has 2 mutable vertices, or if the mutable part of Q is this particular quiver called the Markov quiver, which has a 3-cycle with arrows of weight 2 between each of the vertices. And your mutation sequence is this particular mutation sequence where you just mutate around the cycle periodically. All right, so I had some evidence that this actually holds. Yes, Stephen?
I find this a bit like counterintuitive, because like mutation is an evolution. So if you can go like forwards and get something sign coherent, like why is it that you can go backwards and get, yeah, back to your original quiver, which is arbitrary?
Yeah, so that's a good question. So one thing I guess is that this genericity condition is going to prevent you from sort of starting and going back infinitely many times. But maybe some intuition here is that actually if you look at the class of all possible quivers you can get via mutation, only some like small, maybe connected subset of these is actually not sign coherent. And if you go far enough out, everything is sign coherent. So you can only stay in that region for so long. And I guess, this conjecture is, I'll give you a little preview that it hasn't been proved in full yet. So, maybe you can stay in that little non-sign coherent region for infinitely long, but there are no examples so far.
Okay, thanks.
Yeah.
What does it mean to be like, as because you like producing your consistent constants, such that after that, I don't
Yeah, no, that's a great question. So when they pose this conjecture, they phrase this in terms of just fixing the mutable part of your quiver, and then sort of considering all possible ways that you could add frozens at once. And so there's no uniform bound on how far down the mutation sequence you would need to go that works for all possible ways to add frozens, but you get kind of an asymptotic limit that tells you that any way that I add these frozens, it will eventually become, really after finitely many steps, it will become sign coherent. But we take the perspective of also fixing the frozen data at the start. And so really for us, it's more of an eventual rather than an asymptotic kind of viewpoint. But yes, very good question. Are there any other questions?
So we're certainly two frozens. We're actually slightly confused about how we know that every vertex has one of these two colors. Am I adding arrows from every mutable vertex to at least one of these two frozens? Is that the idea, or am I making sense?
No. Wait. So you're asking? So sorry. Do you want to?
Well, no. Yeah, sure.
So if you have a mutable vertex with no arrows to a frozen, is it red or green or both or neither?
Okay, that's a great question. So we sort of exclude this case from happening, and it turns out that really it doesn't happen in the asymptotic sense. So like asymptotically, your quivers will become complete in the sense that you will always have arrows. There is like a way that you can make sense of this when you don't have, when you just have isolated, I guess frozens, or rather that you have a mutable that is not connected to any of the frozens. I guess in this case, you wouldn't at least be violating sign coherence. You wouldn't say that there exists, this two path from a frozen to a mutable to your frozen. So yeah, I guess you can also work in the setting where you just are not allowing these arrows and just say that you haven't broken sign coherence.
So does that always have a Burcroff vertex attached to the sign coherence protocol?
Wait, sorry, quick here?
Yeah. So if it quivers, so in the principal framing case, it's always tolerable.
Yeah, so in the principal framing case, I think you should never end up in the setting where you have a mutable that is not connected to any frozens. Yeah, so you don't have to deal with that in the principal framing setting. All right. So now let me state a little bit about what Scott and I did in relation to this conjecture. So first, a quick definition. We say that a quiver is mutation infinite. If the set of quivers that you could get to via mutation is infinite. So for things like a rank 2 quiver or this Markov quiver with no frozens, these will be mutation finite because you can check them when you mutate, you just start reversing arrows. Sorry, I should also add an addendum that actually Gekhtman and Nakanishi did all their work in the more general skew symmetrizable matrix setting, but for this talk, we're just restricting quivers. Okay, but what Scott and I looked at is we look at quivers whose mutable part is mutation infinite. We say that if the mutable part is mutation infinite, then the asymptotic sign coherence conjecture holds for random mutation sequences with probability 1. So this is a bit of an interesting statement because it doesn't tell you that any particular mutation sequence gives you this eventually gets you to sign coherent quivers, but it does tell you that if you start mutating your quiver uniformly at random, then if you take a limit as you or a limit in terms of the number of mutations you've done, then almost all of the quivers that you could get to after L mutations will be sign coherent and remain being sign coherent as long as the rest of your mutation sequence is generic enough. All right, and one maybe nice feature about this proof that we don't usually get from sign coherence is that this proof is entirely combinatorial. So I'll give you a little bit of a peek of how this works in just a little bit. And one corollary of this, potentially also using some prior work of work and teams as well, says that if Q mute is mutation infinite, so this same condition, then almost all quivers that are mutation equivalent to Q are sign coherent. So you get almost this probabilistic version of sign coherence via a combinatorial argument, even though all of the existing arguments that get you to the full sign coherence are not combinatorial. So in particular, you could start with the principal framing, and that is exactly the setting of the usual sign coherence conjecture. All right. Yes, Stephen?
An interesting notion of mixing time, like how many mutations you have to do to get sign.
So that is a great question. So I guess there is, one could certainly look at such a notion. We didn't try too hard to bound exactly what this looks like, but I'll go through the method in a little bit. There's these special types of quivers that work and teams study, where you get like some bound on how far away from one of these you are at any given time. And then we give some concrete bound once you find one of these ones on how far you have to go. So there are, or this statement does kind of give you a notion or a bound on what the mixing time should be probabilistically.
Nice.
Okay. So first, let me return to what does generic mean in this statement of the asymptotic sign coherence conjecture. So there are a few properties of a mutation sequence that one could look at. So we say that a mutation sequence is weakly balanced if each vertex is mutated at infinitely many times in that sequence. So we never forget about a vertex. We then say it is balanced if each vertex is mutated a positive proportion of times. And then we say that it is monotone if it is a geodesic in the mutation graph. So another way of saying this monotonicity condition is that each time that I mutate, I'm getting strictly farther away from my initial quiver in terms of the number of mutations that it would take to get back. And the original statement of the ASCC is that generic means balanced and monotone. But they add in a note that weakly balanced is probably enough. Maybe you can insert a weakly here. And actually, at least from our investigations, it seems like one could take even weaker senses of generic, and this should still hold. So it's still kind of maybe an open question to correctly formulate what the most general version of generic could be in order for this property to hold. Sure. And now let me say a little bit about how we actually go about combinatorially understanding this sign coherence phenomenon. So the first step.
Sorry, can I ask, does random imply monotone?
No. So I guess in our models, we are sort of taking a random, or like, I guess maybe the default thing is to do uniformly random. There's like several notions of random you could do. Maybe like one thing is that it's a little bit hard to say exactly what a random monotone sequence would be. But you could take a random sequence and then condense it to a monotone one. Or like almost a random mutation sequence will take you infinitely far from your initial quiver. And then you could take sort of the monotone sub mutation path from that. Thanks. Good question. Yes.
Sorry. What does it mean to say it's mutated a positive proportion of times?
Uh,
All proportions are positive to me somehow, but I must have the wrong notion.
Yeah, I can tell you precisely what this means. So this means that like for all choices of vertices, so these are labeled by 1 through n, then the limit as L goes to infinity of 1 over L times the proportion of times that you are mutating at that particular vertex over probably L. Oh wait. Maybe just that's the correct thing there. That this should be positive. Yeah, this is sort of a weird condition to check though, because you need to then know about the full mutation sequence. All right. But yeah, let me say a little bit about how to get a combinatorial handle on sign coherence. So the first step is that if the mutable part of your quiver is mutation infinite, so exactly this condition that we put on it, then random mutation takes your quiver to something called an ice fork with probability 1. And this step is really an extension of work done by Burcroff in 2014 in his thesis, where he studies these quivers, special quivers called forks. And the ice is just saying that we're extending this notion to the fact that we have frozen vertices present. And I won't go deep into the theory of forks, but these are very useful quivers because they sort of avoid mutation cycles in the sense that once you've mutated your quiver and you get to a fork, as long as you don't go back from it, then I'm guaranteed that all of my mutations are always taking me to quivers I've never seen before. We're never looping back. And so these are sort of very helpful in getting a grasp on the mutation graph. All right, the second step is that once we've gotten to an ice fork, this is kind of the crucial idea, is that an ice fork will become sign coherent after we mutate at all vertices. And then you have to do one more mutation after that. And you will get to something which is sign coherent. And then the third step is just showing that the sign coherence is preserved. All right, and now seems like a good time to maybe actually work through an example of how this works. All right, so here we're taking a rather random quiver. I think some people in this room were involved in helping choose a random set of numbers to generate this. And then we're going to do random mutation. So here, this purple star is going to denote where we are mutating at. Okay, so we mutate. And we started in this first one with a green vertex. And when we mutated, we lost our green vertex. So now all of these vertices are neither red nor green. So sign coherence is sort of not, it can decrease as we mutate. But we keep mutating, and now we have a red vertex. And now two of them are red or green. And we keep mutating. And you'll notice that as we mutate, these numbers of arrows attached between the vertices is increasing, I think, doubly exponentially. So they're going to get really big and really hard to manage very quickly. And this is the typical setting. But we've already, after just a few mutations, we've gotten to this world where this quiver is sign coherent because these two green vertices, all of the arrows from the frozens point away, and that red vertex, all of the arrows from the frozens point towards it. And if you keep mutating, this stays in this world, even though these numbers have gotten astronomically large. All right. Yeah.
We see the ice fork in this example.
So I believe you can see an ice fork in this example. So probably a few steps before it became sign coherent, it is an ice fork. But maybe for now, I don't want to go through why it is an ice fork, but there is like a very concrete combinatorial definition of forks. Yeah. But actually, what I will go through briefly is that this holds much more generally. So this works for a more or a larger class of quivers that we introduce, which we call Bragg quivers. And so this Bragg stands for the rest of my colors. Bragg stands for blue, red, orange, green. And these quivers were introduced to sort of capture these last two properties in a more general way than just for forks. And Bragg quivers have a nice combinatorial description. All right, so first we say a pair of mutable vertices is complementary if they point in opposite directions to any frozen. So in particular, red and green vertices are complementary. And maybe similar to Vincent's talk a little bit earlier, what's going to happen is we're going to add a bit more structure to our quivers in order to more easily see why these two properties should hold. So 2 and 3. So what we said is that a quiver is Bragg if all vertices can be colored blue, red, orange, or green, such that red and green are as usual. So it's exactly the same notion as before. We want that blue and orange vertices are complementary. And lastly, what we want is that whenever there is an arrow between two mutables, the arrows point in the prescribed directions. So what we get here is we get a little diamond, where we go in the usual order of blue, red, orange, and green. And arrows will go clockwise around. So what this is saying is that whenever I have an arrow between the blue and red, it has to point from the blue to the red. And the same for each of these pairs, but we are not imposing any restrictions between red and green or blue and orange. Okay. And some features that I'll just mention quickly is that quivers can quickly become frog. After a single nice mutation. So there's some technical description of what nice means here. But then it's also fairly easy to see, once you have the theory correct, that frog quivers quickly become sign coherent. And so the way to see this is that under mild conditions on your frog quiver, red and green will stay red and green. No matter what mutation we're doing. So the sign coherent vertices are sort of preserved. And then what we get is that blue vertices turn orange after mutation at that vertex. And orange vertices turn red or green after a mutation other than at that vertex. So mutation away from it. Okay. And it's not so hard to convince yourself that if you play this game, then once you've mutated at every vertex and then done one additional mutation, you will get to a quiver that is sign coherent. And so just to do one quick example of this, so thank you. All right, so now we're going to revisit the same example we had before, but through the lens of frog quivers. So here we start with a green vertex, and this quiver is not yet frog because no matter how you assign colors to those two uncolored ones, they will violate one of those rules. And we mutate, and this mutation was not good because now we are still not frog, but this next mutation is one of our nice mutations. And so our quiver has now become frog, where it has one red vertex, an orange, and a blue. And now when we mutate at the red vertex, these rules tell us that the orange has to become red or green, and indeed it becomes red. And then now we're mutating at the blue vertex, which tells us that it becomes orange. And then lastly, we mutate at the red vertex, which will turn that orange one red or green. And now that it's all red or green, it has to stay that way. So this kind of captures exactly what's going on for sign coherence in these particular types of quivers. And then just to quickly write one last theorem here is that if we take a quiver whose mutable part is what is called mutation abundant. So this means that every quiver in the mutation class, or every quiver that we can get by mutating it, has arrows of weight at least 2. So we don't see any zeros or ones. So in this case, and we also want to restrict here to just rank 3. Then we get that the full asymptotic sign coherence conjecture holds for these set of quivers using this frog technology. And so kind of a few upshots of this. So one is that this asymptotic sign coherence conjecture is still open, but now we have some evidence that it really holds in lots of cases. So it's, now maybe even more intriguing to study why this holds, or maybe this gives some restriction on where it could fail. The second thing is that lots of people, when constructing quivers in order to make their cluster algebra, you start with something which might not be equivalent to a principal extension, but sign coherence phenomenon, or sign coherence might still be something that is useful to you. And this broad condition is very explicit and combinatorial and kind of captures that coherence. And so it could be interesting to study for these kind of natural classes of quivers, when are they broad? And then lastly, this is kind of given a little bit of progress towards understanding sign coherence more generally, combinatorially. And so it's still to be seen how far this can be pushed. Oh, thank you for your attention.
Thank you, Amanda. Are there any questions or additional questions?
Okay. I just want to comment. So the question is, it's like I don't quite understand that complementary. Just any, yeah. So it's like for all frozens that they have arrows too, they point in opposite directions.
Yes, I guess maybe one of these mild conditions that we care about is completeness, which again, like you can get to after usually like a few mutations. So yeah, maybe technically one should say for all the frozens that they point to. But also this is kind of in the case where you restrict it to frozens.
Okay, so you put okay, you restrict it to frozens and so either a condition on if they have arrows to one frozen, it's just the condition about those arrows, and if they have arrows to both, then it's a condition on the arrows to both.
Yes. But I guess one could also extend this notion quite naturally to looking at all the frozens at once, but like you say that that this is because this opposite condition is for each frozen, so it still makes sense to define that, and it might take more mutations in order for your quiver to become broad with respect to all of the frozens, but you can do that and it still makes sense, and then the argument still goes through.
And then the comment is, if you consider switching from foo to U-shot.
That's a very good point. Is fuchsia like complementary to orange though? Because yeah. I should mention I don't have it at hand, but I can show you later. There is a creature called a brog that shows up in some video game called Xenoblade. It's kind of like a mixture between a bunny and a frog, or like a bog frog. So if you search frog, you will see some lovely pictures of a frog like
viable. Help me understand that.
Yeah, so
How's the conjecture falsifiable? Because it's just maybe I haven't gone far enough and keep on going farther and farther.
yeah, so that's fair. So how would one falsify this asymptotic sign coherence conjecture? So yes, we one complaint one might have is in order to ensure that your thing is not generic, maybe depending on your genericity, this is hard, but here we have like this explicit notion of what counts as a generic sequence. And then in order to falsify this, one would need to control for all quivers in that sequence. So, maybe you would need to find some pattern among the frozen data such that you could guarantee that you always have this two path that breaks or from frozen to mutable to frozen that breaks sign coherence. So in theory, you can just construct something and maybe put or be able to prescribe the arrow directions after each mutation in some way that violates this, but no one has done this yet.
In the notation of principal framing, are we starting with the quiver with only mutable vertices?
Yes.
This one. So I guess are there any conjectures on like there's perhaps like more than one frozen vertex per mutable vertex, or perhaps like if there's like sort of asymmetry in the number of frozen versus mutable?
So there is a sort of equivalent framing of the sign coherence phenomenon, which just says if you start with a quiver where all of the vertices are either all green or all red. So there you could have arbitrarily many frozens. And you know, those frozens might point to multiple different mutables, but if you start with everything being simultaneously green or simultaneously red, then you get to keep sign coherence. And this can kind of be seen because you can like combine or split up frozen arrows in a way that is kind of compatible with the mutation relation. So there is a version that maybe isn't quite this principal framing, but nothing is known outside of the simultaneously green or simultaneously red, I think.
If there are no more questions, let us take a moment again.